Okay, I will show you how to create the plots that we need for our paper number 1, and how to export the data, how to show that the electric field and the potential is indeed a function of as a function expected from a point charge. Okay, so we have a point charge, a small circle in 2 dimension, and a large circle outside. We set the potential is 0. Inside we set the potential 10 volts, and we got the electric potential and then electric field plots. Okay, so now automatically it gives the potential plots. I mean, to add the electric field to that, you just do right click and then do arrow surface. And once you get the arrow surface, the X and Y component of the electric field is most likely pre-populated. And when you say plot, you will see the electric field vectors. Now, what we want is we want to compare electric field magnitude and the electric potential value as a function of distance from the center of this point charge, center of the small circle. Okay, so what we can do is we can do a cut line. Okay, so I already did here, but I will show you. You just go to data sets, right click, cut line 2D. Okay, now once you have it, it asks you to give 2 points, the start point and the end point for the cut line. Now, since we set a small circle emulating a point charge, and we made that copper, a metal, we know that the electric field inside should be 0. So in my original descriptions of this process, I set the start point outside the little circle in the center. So that's why it's 0.10 to 10. Okay, but you have to be careful. If you do that, when you export the data, when you do a plot, and which I will show you now, you can go to results, go to 1D plot group, and then add a line graph. Now, in your 1D plot group for the data set, you can select Cutline 2D1. And if I go to Cutline 2D1, and plot it, it will show you it's outside. It starts outside the central circle, which emulates a point charge. So, so in my line graph here, this one plots potential as a function of. Now, as you see, 0, and then it says arc length. What arc length is, this cut line that I have created, the start point is taken to be 0, end point is whatever length it is, taken to be the end point. So it's not plotting from the center of the circle. It's not plotting from where exactly the point charge sits. So, however, in our formula, when we have 1/4 pi epsilon naught Q over R for electric potential, that R is measured from the exact location of the point charge or from the center of this circle. So that is a confusion. So what we can do, we can actually set this point from 0, 0 to, from center to the outer edge, as you see here, from center to outer edge. When we go to the plot here, then you will see a constant potential at 10 volts as expected, because that's the conductor. It's a equipotential. So at 10 volts up to the outer perimeter of the circle, and then it starts going down. Again, our goal is when you're outside that circle, when you're outside the point charge that we created, is it a function of 1 over r, right? That's what we want to understand here. Is it going down as a function of 1 over r? This potential function, does it obey 1 over r, right, as it goes down? So that's our goal. Similarly, we can create another plot group. Go to results, right click, 1D plot group. And here, I'm going to select Cutline 2D1. And then I would like to add a line graph, but this time I'm going to change it to electric field. So you go to component, electrostatics, electric field norm, which means the magnitude of the electric field vector. Okay, and then say plot. So now what you see is electric field is 0, and then immediately when you get outside that copper circle, it becomes higher and then goes down. Again, what we want to do is we want to verify if this is 1 over r squared. Now, I showed in multiple occasions that we can do a log-log plot. And if the log-log plot for a r to the minus 2 dependence shows a slope of -2, then that, it should be, first of all, a linear dependence. And second, if you fit that to a line, the slope needs to be -2. That means it goes with 1 over r squared, as expected from, say, Coulomb's law. So same thing for the potential. If it, first of all, it needs to be linear. And second, if the slope is -1, then it's expected to be 1 over r dependence, and it's correct. So, okay, you can see in Comsol whether these, let's say for this electric field, so let me change this electric field. And this one is electric potential. So for the electric field, what I can do a log scale here, x-axis log scale, y-axis log scale. And if I do that, okay, remember all this region, and I don't need those parts. This is inside the circle, okay? So I can just change that x minimum, say put 1e minus 2, which is 10 to the minus 2, right? Okay. So, so now, and then for y, maybe I should also change that to, like, say 10 to the 2 as minimum, or as maximum. 10 to the 2 as minimum. Okay, so now this region, right, 0.05 is the radius of my circle. Okay, right outside my circle, as you see, I see a linear dependence. Okay, so I want to export the data here, and then I want to understand whether the slope of this is -2 or not. Okay, so you can export this as a text file and then put it on, say, Excel, Mathematica, Python, MATLAB, Igor Pro, whatever your favorite data analysis software is, and check if the slope is -2. All right, I'm going to show how to export that. Okay, so you go to export, right click, plot. Okay, so in this case, I'm going to select electric field. Okay, line graph 1. That's the one I want to, okay, it's text file. I browse and say, let me just give it a name. E field versus R. And then I'm going to select here CSV file. I like comma separated values, easier. It will automatically open in Excel, for example, and then save that. But we are not done. We need to also click on export. Okay, once we have that, then we can go ahead and analyze our data. Okay. So, okay. Now, when we did the export, it saved the file in the folder that I designated here. Now let's go ahead and pull that file and put it in Excel or Mathematica and try to do a line fit. Okay, so here is what I will show you how it looks. So if you click on the file, this is my file name here. And this is what opens the CSV file. Again, it starts from 0, that's the center. But again, these are extremely small values, which means practically inside the conductor, the field was 0. And then this is where we start seeing actual large values of electric potential. And that's at 0.05, okay? So I think in this case, electric field, not electric potential. Okay, this is electric field. So it should go 1 over r squared if it is a point charge. Okay, so this is 0.05 and this is where it starts. So I don't need anything other than, so it should start, my values should start 0.05 in this case, because these are really inside the conductor. I'm not interested in those. Okay, so what I'm going to do, I will just copy these because that's what I need. And click another one here, another sheet, and then paste it there. So this is what I need. So I'm going to save it to a CSV file from here. If you prefer to do it in Excel, if you are comfortable with that, you can do it here. Just create a chart. I mean, you can say chart and a scatter plot. And then you see it goes like this. And then you can take the log of these here as well. So log of both, right? I can write here log of, all right, log 10, let's say, of this. And then just double click. Same thing here, log 10 of the next column. And then evaluate it for all of them. So we can select these, again, insert the log plot. Okay, here we go. And it's a line, you see, it's a linear. Okay, if you like, you can use this after taking the logs and then do the line fit here, find out what the correct, slope is. I'm gonna do it in Mathematica. So I'm gonna transfer these to Mathematica. So I'm gonna, so these log values, I can take them and then put it in Mathematica, or I can take the original values, it doesn't matter. So let me take the log values and then click and then create another sheet, put them here. Oh, okay, because they are calculated, I need to do paste special. I just need the values. Okay, and then I'm gonna save this as a CSV file, save as, comma separated. Let me give another name. Okay, that's fine. So now I'm gonna go to Mathematica, and I already did some testing here, but let me start a new notebook. Okay, so I need to import that into data. Okay, let me call it data 1. Import, let me make this a little larger here. Okay, then I do that, and then I go to file browser, my folder here, and this is the file I saved. Say choose, and then close that and shift enter. That's Mathematica. Okay, so the data is now transferred to Mathematica. Okay, this is the list, and to check, you can do a list plot in Mathematica of this data 1. Indeed, it's a line. Okay, that's as expected. So is the slope -2 or something else? That's what I need to figure out now. Okay, in Mathematica, if you want to do fit, there's a function called fit. Okay, so I'm going to call this line 1, and that's equal to fit. Okay, so what are we fitting? The data 1, that's what we're fitting. And then I need to enter a few pieces of information. So what type of function I'm fitting? Okay, Mathematica, if you take this like 1x, it treats this as like a1 plus like a0 plus a1x plus a2x squared. So if I want to fit a parabolic function, for example, I would go like this, and cubic function, I would add these. But in this case, it's a line. So, and my theory dictates that it should be a line. So that's what I'm doing. And my goal is to find whether the slope is equal to, in this case, -2. Okay, and then x is the variable. All right, so this is the syntax. Now let's do that. All right, so this is my function that I get out of this. So 2.5 minus, and as you see, as this is -1 times x. So it didn't give me -2, but it gave me -1. It is linear. That aspect is good as expected, but it is slope is -1. And again, your assignment is to think about why this is so, and you know, what is essentially we are simulating in Comsol, and how do we remedy the situation? How can we really simulate a single point charge? Okay, that's your assignment. So this is for electric field, and you need to repeat the same thing for the electric potential. Okay, so now I want to put my fit in the same graph with my data, and I can do that. I will do here is show. I gave a name to my plot 1. So I can just say, okay, show me plot 1 together with, now I want to plot this function, this line 1 function that I just got out of the fit here. So I'm going to say plot, and that's line 1. And then I need to give the horizontal independent variable here. So it starts around -1.4. This is the log, remember, and then it goes all the way to 0. Okay, so this is what I need to plot. Okay, oops. Let me see what I did wrong here. Oh, okay, I found a mistake and corrected it already. So I didn't enter the x, which is the variable that's needed. This is the x variable that I have, and -1.4 to 0. And indeed, you see it's a perfect linear fit. However, the slope is -1. That is your job to explain. So this is one way of doing it. Again, you don't have to do it in Mathematica. You can do it directly in Excel, or Igor Pro is one of my other favorite programs. MATLAB, Python, whatever you're comfortable with. You know, once you export that CSV file, you can import it into anything where you can do a linear fit, determine the slope, and then put the fit along with the data on the same graph overlaid. Obviously, I'm not doing it here, but do the axis labels, everything. So make a complete graph to put in your paper document, which you will do in overleaf.com using LaTeX. Okay, I hope this answered quite a few questions on Comsol, how to do the graph, Cutline. And the important thing is it should be measured from the center of that little circle that we created to represent the point charge. Okay, and that, I think, hopefully answers some questions. And feel free to contact me if you need any more help.